So we just saw how to get the selection rules for spectroscopy, and let's just summarize what we have seen so far. So suppose you want a spectroscopic transition from one state denoted by psi 1 to another state denoted by psi 2. Okay. Then this spectroscopic transition, the intensity of this transition is proportional to a quantity called psi 1, and I'll just say alpha here, and I'll say psi 2 d tau. Okay, where alpha can be x, y, or z for electric dipole transition. Okay, so for electric dipole transitions, alpha is either x, y, or z. Okay, for other transitions, it can be x square, x y, y square, etc. Okay, so x z, y z for other transitions. So if you look at Raman spectroscopy, okay, then the transition is related to the polarizability, and so you might have terms like x square, x y, y square, x z, and so on. But essentially you have integrals of the form psi 1 alpha psi 2, okay, where alpha is typically one of these quantities. Now this quantity, if this is not equal to 0, okay, if this is not equal to 0, then the transition is allowed. The transition from 1 to 2 is allowed. Okay. So now how do you find out whether this should be equal to or not equal to 0? Okay. And the simple rules, you can just look at this integrals, and you can use what we learnt in the last class about integrals. So this integral, if psi 1 belongs to irreducible representation gamma 1 and psi 2 belongs to irreducible representation gamma 2, and let us say alpha belongs to irreducible representation gamma alpha. Okay. If each of these belong to some irreducible representation, okay, then this integral will be non-zero only if this direct product, okay, then integral not equal to 0 if gamma 1 direct product with gamma alpha direct product with gamma 2, if this direct product contains the totally symmetric representation. Okay, so this direct product, this integrand should be totally symmetric. Okay, should contain the totally symmetric representation. Okay, so that is a simple condition. Okay, and also or in other words, okay, using again we go back to the theorem we had about direct products. In other words, your gamma 1 cross gamma 2. Okay, so this representation, this direct product, okay, should contain gamma alpha. Okay, so the representation, the direct product representation of 1 and 2, okay, should contain the representation of alpha. Okay, so that's the so these are the general rules, and if this is satisfied, then this integral will not be equal to 0 and the spectroscopic transition will be allowed. Okay. So now let us see a simple application of this. Let us look at vibrational spectroscopy. So example, spectroscopy from psi 0 to psi 1. Okay. So, you are looking at a transition that goes from psi 0 to psi 1. Okay. These are two vibrational states. Okay. And psi 0 is totally symmetric. Okay. So, psi 0 is a totally symmetric, psi 0 belongs to the totally symmetric representation. Okay. So that means psi 0 belongs to the totally symmetric representation. Now, question is, to which representation can psi 1 belong to in group C4b? Okay. To which representation can psi 1 belong to in group C4b? Okay. And you can, so the question is, you want to look for transitions from psi 0 to psi 1. Okay. So and you are told that psi 0 is totally symmetric, then to which representation can psi 1 belong if you are in this group C4b? Okay. Now, this can be answered very easily if we look at the character tables. So, if you look at the character table of C4b, C4b has E, the identity, and then it has 2 C4, C2, two sigma V and 2 sigma D. Okay, and so the order of the group is 8. The order of the group is 8, and the order of the irreducible representations are 1, 1. There's A1 and A2 are one dimensional representations, as are B1 and B2, and E is a two dimensional representation. Okay, the characters of A1 are, A1 is a totally symmetric representation. The characters of A2 are 1, 1, 1, minus 1, minus 1. Characters of B1, so should be 1, 1, and then two of these can be minus 1. I'll just check. Minus 1, minus 1. So it should be minus 1, 1, minus 1, and B2 will be 1, 1, minus 1, minus 1, 1, and E is 2, 0, 2, 0, 0. Two 0 minus 2 0 0 minus 2 0 0. Okay. So these are the characters of the various representations, and you can just start from this and you can quickly see, you can immediately see that in this column, okay, Z belongs to the totally symmetric representation, RZ belongs to A2, okay, and XY belong to E, XY or RX, RY. So X and Y together form a basis for this representation, as do Rx and Ry. Okay. And for as far as the products go, you have x square plus y square and z square, and then x square minus y square, then you have xy, xz, yz, yz. Okay. So these are the products. So xz and yz together form a basis for this two-dimensional representation, and xy forms a basis for b2. X square minus y square forms a basis for b1. Okay. Okay. So now using this table, you can very quickly answer this question. So now first let's look at dipole transition. Let's look at dipole allowed transition. So first, dipole allowed transitions. Okay. Now and in this we will look at z. Okay. Now z belongs to A1. So then the integral psi 0 z psi 1 d tau. Okay. This is not equal to 0. Not equal to 0 if gamma 0 gamma z cross gamma 1, okay, contains A1. Okay. Now you are already told that gamma 0 is the totally symmetric representation. So in other words, A1 cross and gamma z belongs to A1. So A1 direct product with A1, direct product with gamma 1 should contain A1. Okay. Now you can immediately see that if I take a direct product of A1 and A1, I will get back A1. Okay. Both these are one dimensional representation, so their direct products will just give me A1. Okay. So A1 direct product with gamma 1 will just give me gamma 1. Okay. So in other words, gamma 1 should contain A1. Since A1 is a totally symmetric representation, a direct product of A1 with gamma 1 will just give me whatever representation gamma 1 is. Okay. So in other words, gamma 1 should contain A1 or gamma 1 equal to A1. Okay. So if gamma 1 is irreducible. Okay. So to which irreducible? So if we say irreducible representation, okay, the only irreducible representation to which psi 1 can belong is A1. Okay. So if you want to see a vibrational excitation polarized by Z, then psi 1 has to belong to A1. Okay. So psi 1 has to belong to A1. Okay. Okay. Now the other case you can have is xy polarized. Okay, you can have a transition that is xy polarized, and in this case xy forms a basis for E. So you do the same thing, then you say that A1, so A1 instead of gamma z you have gamma xy. Gamma xy is nothing but E gamma 1. Okay, this should contain A1. Okay. Now you can look at this and you can immediately identify the following, that suppose I take A1 times E, I will just get E cross gamma 1. Okay. Now you have a direct product of E and gamma 1. Now you look at the characters of E, they are 0 on these two terms are 0. Okay. And it's only these two terms that are non-zero. So these three terms are 0 and only these two terms are non-zero. Only these two characters are non-zero. Okay. So if I take a direct product of E with any of these representations. If I take a direct product with A1, I'll just get E. Okay, so therefore gamma 1, so gamma 1 not equal to A1. Okay, because clearly if I take a direct product of E with gamma 1, I'll just get E, and E does not contain A1 because E itself is irreducible. Okay. Then what happens if I take a direct product with A2? So E direct product with A2, so the characters will be 2 into 1 0 minus 2 into 1 0 0. So you'll get back E. Okay, so again so E into gamma, E into A2 is also identity. So E into A1, so E direct product A1 is equal to E direct product A2 equal to E. Okay, and that's why gamma 1 cannot be equal to A1 or A2. What about B and similarly you can see that E direct product of E with B1 is equal to direct product of E with B2. Okay, in all the cases you'll just get back E. Okay, so if I take E B2 for example, so I just get 2 0 minus 2 0 0. Okay, so essentially E cannot be A1 A2 B1 B2. Okay, so the only possibility is gamma 1 equal to E. So gamma 1 cannot be equal to A1 A2 B1 or B2. So now can gamma 1, can we have gamma 1 equal to E? Okay, so that is a question. Okay, so if gamma 1 is equal to E, then E cross E direct product with gamma 1 is just it will be 4 0 4 0 0. Okay, so E, so I'll do it right here. So E cross E, okay, we will have characters 4 0 4 0 0. Okay. Now the question is, does this contain the totally symmetric representation? Okay, so does E cross E contain A1? Okay, and it's not hard, and this is where we use our earlier theorem. Okay, so we want to know how many times A1 appears in the reducible representation E cross E. Okay, so we'll go back to our earlier theorem, which we said how many times an irreducible representation appears in a reducible representation. How many times does A1 appear in E cross E? Okay, so E cross E is this, E cross E has these characters, A1 has these characters, and if you want to find out how many times A1 appears in E cross E, then the answer is A is equal to 1 by H sum over all R chi of A1 of R chi E cross E of R. Okay, so you just take a product of the characters, okay, in A1 and E, and you can immediately see. So if I take 4 into 1 plus 0 into 1 plus 4 into 1. Okay, so you have 4 into 1 plus 0 into 1 plus 4 into 1 plus 0 into 1 plus 0 into 1. Okay, so and H is equal to 8, so this is equal to 1. Okay. So that means E cross E contains A1 or A1. Okay. Okay, so since E cross E contains A1, that means A1 cross E contains A1. That means psi can be, psi 1 can be in E. Okay. So what we conclude from this is that the dipole allowed transitions are, there are two possible dipole allowed transition. Psi 1 can belong to A1, and that will be a dipole polarized along in the z direction, or psi 1 can be E, psi 1 can be E, and that will be polarized in the xy plane. Okay. So these are the two possible dipole allowed transitions, and just as we did this, we can also find what are the other transitions, those that are Raman active and so on. Okay, by looking at the products to find out which of the products appear in which representations. Okay, so clearly, if psi 1 is in A1, then you can have transitions involving x square plus y square and z square. Okay, or if psi 1 is in if psi 1 is E, you can have transitions involving x z y z, okay, involving the x z y z, okay, and so on. So this method of identifying which transitions are allowed and which are not allowed is something that can be done extremely easily using the character table. Okay, so this is one of the most important applications of group theory, and what we should mention here is that we just ask the question to which representation psi 1 can belong. Okay, so we just asked to which of these representations, to which of these irreducible representations psi 1 can belong. Okay. Now this is only part of the story, so you cannot this still in any real molecule. Suppose you have a molecule belonging to C4V, okay, then what you have in molecules are what are called normal modes. Okay, so you have normal modes of vibration, and in each normal mode of vibration, it could be things like symmetric stretch, anti-symmetric stretch, it could be bends, and these are the various normal modes of vibration. So what you have to identify is not you have to look at the normal modes, and you have to see to which normal modes or which normal modes belong to which of these representations. Okay, so the ground state of one normal mode might belong to one representation, the excited state of a normal mode might belong to a different representation, and so on. Okay, so it's not as straightforward as just saying that this wave function is symmetric and so on. You really have to look at each normal mode, and you have to see to which representation each normal mode belongs. Okay, but once you have identified to which representation each normal mode belongs, then you can go ahead and use these simple rules to identify which of the spectroscopic transitions are allowed and which are not allowed. So far we have seen two applications of these character tables. One is in identifying which overlap integrals relating to energy are non-zero, and the second is to identify which are the spectroscopic transitions that are allowed or disallowed. So now we are going to discuss a concept that is widely used in various applications of group theory and quantum chemistry. This is called symmetry adapted linear combinations, and sometimes it's denoted by SALC. Now you might have seen you might have already seen some applications of this, and we'll also see how to use this in some applications. You might have heard of linear combination of atomic orbitals giving molecular orbitals. Okay, so this is a theory called LCAO-MO. And here what you do is you take your atomic orbitals, and by making suitable linear combinations of those atomic orbitals, you construct molecular orbitals. Okay. So then the question is which atomic orbitals do you use to construct which molecular orbitals? So suppose I want a certain molecular orbital, which are the atomic orbitals which I should use to do these linear combinations? And one of the things that we'll use is that the atomic orbitals that are used to make the linear combination should have should have the appropriate symmetry of the molecule, okay? And we'll see examples of this. The other problem in which symmetry adapted linear combinations are widely used is in studying the normal modes of vibration. So suppose you have a polyatomic molecule, then you have a large number of vibrational degrees of freedom, and the vibrational degrees of freedom are the independent vibrations are what are called as normal modes. Okay? So which are the coordinates within the molecule? Which are the coordinates within the molecule which behave independently during these vibrations? Okay, so which are the coordinates in the molecule corresponding to these normal modes? And it turns out that normal modes are nothing but linear combinations of the coordinates of the atoms, and then so we need those linear combinations that again satisfy the symmetry of the molecule. Okay, so another example is let's say you have an atom in a crystal field, okay, or in the field due to a ligand, and you know that in this ligand field there is a splitting of orbitals that takes place, and how should the splitting takes place? Okay, so what is the basis for the splitting? That is another place where these symmetry adapted linear combinations are seen. And so what the common feature is that you have linear combinations of various atomic orbitals or coordinates, okay? And these linear combinations should have symmetry of molecule. Okay. So you should choose those appropriate linear combinations that have the symmetry which the molecule shows. Okay. And so this is the idea behind symmetry adapted linear combinations, and it will become clear as we look at more examples. Okay. So in order to so the question is, how do you find the appropriate orbitals of which you should take a linear combination, or how do you find the appropriate basis vectors with which you take these linear combinations? Okay, so what are the appropriate basis functions whose linear combinations we take? Okay. So what are the appropriate basis functions whose linear combinations we take for whichever problem of interest? Okay. So the answer to this is you choose those basis functions that are symmetry adapted. Okay, so you choose so this linear combination is called a symmetry adapted linear combination. Okay. Now, in order to identify this, in order to work out these symmetry adapted linear combinations, we shall use a very useful concept which you have seen before when you were doing vectors. That is called the projection operators. Okay. So you might have seen this in quantum mechanics. You have definitely seen projections when you were dealing with vectors. So the way to think of it is that if you have a vector v, you want to find the projection of this vector along another vector u. Okay, suppose you want to find the projection of this vector along another vector u, then you just see the component of this in this direction. So this is projection of vector v along direction u. So this is projection, that is, I'll just show it. vector v along u. So that's a general idea of projections when we are dealing with vectors. Now this is also you can write this as v dot u. So v dot u is v times u times cos theta. Okay. So you have to divide this by the length of u. So that will give you the projection along this direction. Okay. So we can work this out, and if this angle is theta, then this is just v length of v times cos theta. Okay. So this is the usual projection we talk about when we are dealing with vectors. Now when we were discussing linear algebra, we said that this vector can be generalized. The idea of a vector can be generalized. You can have functions be treated as vectors depending on the space that you're interested in. Okay. So in such cases, what is the more general definition of the projection operator, and especially when we use wave functions as our basis. Okay. So that's what we are going to look at next. So suppose we have wave functions. I'll denote them by phi j I. Okay, so this is basically wave functions of the form phi 1i, phi 2i, and so on. A whole set of wave functions. Now, what this stands for is this is the jth basis function, and this is the ith irreducible representation. So it is so you have an irreducible representation denoted by gamma I. So irreducible representation is gamma I. Okay. And in this irreducible representation, okay, there is a set of basis functions denoted by phi j I. Okay, so it could be phi 1i, phi 2i, and so on. Okay. Now, so these basis functions are denoted this way. Now, and let's say group dimension of gamma I has dimension Li in group of order H. Okay, so H is the order of the group and Li is the dimension of gamma I. So we have gamma I, which is a representation of dimension Li. So, for example, Li could be a one-dimensional representation, Li could be a two-dimensional representation, like we have seen the various representations like A1, A2, E. Okay? So, this is one of those representations, and the dimension is Li. So, A1 would be a one-dimensional representation, A2 would also be a one-dimensional representation, whereas E would be a two-dimensional representation. And the order of the group is H. Okay? Now, if you have this, then any symmetry operation. So corresponding to a symmetry operation, we can write an operator operating on some arbitrary function. I'll just denote it by phi j I. Okay. So when a symmetry operator operates on some function, okay, what you get is some linear combinations. Okay, you get a linear combination of the basis functions. Okay, so the effect of a symmetry operation on a basis function is to give a linear combination of basis functions. Okay, so we can write this as phi k I. So in the same representation, you have a linear combination sum over all k. Okay. R is the symmetry operation. So R is a symmetry operation, and so when it acts on a basis function, you get typically you get a linear combination. So you have sum over k phi ki times the coefficient, and the coefficient is nothing but the matrix element of this symmetry operation. Okay, and which matrix element it is? So it is the matrix element in representation I, okay, corresponding to irreducible representation I, and the matrix element, it should be so this is phi j, jth basis. So the appropriate matrix element will be the kjth matrix element. Okay. So this is how the in this representation I, the matrix elements are defined as in this form. Okay, matrix elements of any operator. Okay. So this is in some sense the definition of your gamma R phi kj. And if you recall, this was the object that appeared in the great orthogonality theorem. Okay, so every operator can be represented by a matrix, okay, whose dimension will be Li in that representation, and this is the kjth element of that matrix. Okay, so this is the kjth matrix element of R in representation gamma I. Okay. So what I mean is that you have R in this representation gamma I. R can be represented as a matrix, and this is the kjth matrix element. So this is the usual definition of the matrix elements. Okay. But what we have seen is we have looked at it as how this operator acts on a basis function. Okay. Now we'll use this to motivate the definition of the projection operator. Okay. And in order to define the projection operator, let's pre-multiply on both sides. Okay. So pre-multiply on both sides. Okay. Pre-multiply on both sides by the complex conjugate of one other matrix element. Okay. And then we use the great orthogonality theorem. So what we do is shown here. So first we pre-multiply by gamma R, okay, in the nth representation and the k prime j prime element. Okay. So notice that here you have the ith representation, and there you have the nth representation. Here you have kj, and here you have k prime j prime. Okay. So you multiply by the complex conjugate of that. Okay. And then you sum over all the operations. Sum over all the operations. Now, and you do this on both sides. Okay, so on the left hand side, what you have is this object. Okay, so you have sum over R, gamma R, L, k prime j prime star, and you have an R phi I, R phi j I. Okay, so this R phi j I, you have it here. On the right hand side, when you do this, I interchange the sum over k and sum over R, and I write it in this form. Okay, so I have the sum over R coming from here, gamma R L k prime j prime coming from here with the star. Okay, and I have the gamma R I k j which came from here. Okay, and I have the phi k I, which is right here. Okay, so this is the usual way in which you calculate coefficients in any basis function expansion. This is the way you calculate the coefficients. But we are going to use this as a motivation to define the projection operator. Okay. So now we can use the great orthogonality theorem for this, and what you'll be left with is what will come when you use this whole object can be simplified. Okay, it can be simplified, and what you get is h by Li. Okay, Li is the dimension of the ith irreducible representation. Okay, and then you get phi ki. Okay, this phi ki as it is, and then you have these delta function. So delta k prime has to be equal to k, j prime has to be equal to j, L has to be equal to I. So this is the expression, and you have a sum over k of phi ki delta k prime. So you can do this sum over k and you'll get h by li phi k prime of I delta j prime delta li. So this is actually not very complicated. Now what we do is we look at the right hand side and we take this li by h to the right hand side, to the left hand side. Okay, so when you take li by h to the left hand side, then what you have is li by h sum over r. You have gamma r in the nth representation k prime j prime r, which was the operation that we considered. This whole thing operating on phi j I. This whole thing operating on phi j I. And now you can actually think of it in a slightly different way. You can put this. You can imagine that this whole thing is. You can have this thing operating on r phi I. Okay. And the right hand side gives phi k prime I delta j prime delta li. Okay, so what is happening here? Okay, this is an arbitrary vector, arbitrary function. And so if you think of this as some arbitrary function, then this operator acting on this arbitrary function, okay, gives you various delta functions, and it gives this a function in the ith representation, okay, in the ith irreducible representation, and it gives something related to the k prime basis function. Okay, so this operator is called this operator you think of as the projection operator. Okay, so the way you think of this is E. This is a projection onto the nth irreducible representation, okay, and it projects the k prime j prime element. So onto the k prime j prime element, okay, and this, when operated on some function phi j I, this projection, this operator acting on this function, okay, so it takes it from this is a basis function in the ith representation, it takes it to the nth representation. So what you get out of this is phi k prime I, which is same as phi k prime L. Okay, so I can write this as phi k prime L. Okay. So I go from the nth representation to the ith representation, okay, and what I have is delta j prime and delta L. So this is the basic idea of projection. So you project an arbitrary vector and you project it and you get a vector in this representation. Okay, so you get so from an arbitrary vector you can extract what is the component of that vector in a particular representation. Okay, so this is the gist of this. So just as in this case you had an arbitrary vector v and you found the projection along u. Okay, so the same way you had a basis function in some representation. Okay, or you could even take an arbitrary basis function. You could take an arbitrary function and you could project it. You could find what is the projection onto a certain representation. Okay, so this is an object that will turn out to be very useful in constructing the symmetry adapted linear combinations. Now let's consider the case where k prime and j prime are the same. So when k prime and j prime are the same, then this has the expression. So P L k prime phi j and this is equal to phi k prime I k prime q, and you have delta IL delta, and what you had is delta j prime. J k in this case. Okay. So j prime is just k, so delta j k. So instead of j prime you have k. So what you have on the right hand side is phi L k prime. Okay, delta, instead of j prime you have k, so delta j k delta L. Okay. So this is a k prime element. So this is diagonal elements. So notice now we had a so in the expression for the projection operator, you will involve only the diagonal elements of the matrix. Okay, so this involves only the diagonal elements of the matrix. Gamma matrix and matrix. So in this matrix representation, this will involve only the diagonal elements. Okay, only the diagonal elements will be involved in this. Okay, and this expression is also, it turns out to be extremely useful. So just using the diagonal elements, we can find the. So if you just know the diagonal elements of the matrix, you can find the projection operators. Okay, so this is something we will see, and what this one point we should make here is that in order to find projection operators, we need entire gamma matrix. Okay. So that means you need the entire matrix. You need the entire matrix for the representation of every operation. So in any irreducible representation, you have a matrix corresponding to that irreducible representation, and you need all the elements. Okay, this is now if you remember, if you recall, in the character table that you used, okay, you only have trace. So in the character table, only chi I of r appears. Okay. And chi I of r is equal to gamma I of r L sum over L. Okay. So it is a sum of the diagonal elements of this matrix. Okay. But now, in order to find the suitable projection operators, what you find is that it's not enough to know just a trace, but you need the entire matrix. Okay, and so in a sense, if you truly want to find out all these projections and do the symmetry adapted linear combinations, it is not sufficient to have just the character table of the group. Okay, you need more information than just the character table of the group. Okay, but what we'll see in some applications is that because you can use the diagonal elements, you can find, with a few manipulations, just starting with the character table, you can get a large number of projection operators, and there are just a few other projection operators for which you need to do something more than just using the character table. Okay, so that's what we are going to see next. Another point I want to make is that if you have a one-dimensional representation, so for a one-dimensional representation, so chi I of r is equal to gamma I of r. So the matrix, since it's just a one-dimensional matrix, is just a scalar. So the trace is nothing but the scalar itself. And so knowing the trace is definitely sufficient. So for a one-dimensional representation, you can entirely calculate all the projection operators. Okay? But for higher dimensional representations, you need more than just the trace. You need more than just the trace. You need to know the actual matrix elements. Okay? You need to know the actual matrix elements in order to derive the projection operators. Okay? So next class we'll look at some examples of actual calculations on these projection operators. Okay? And then we'll go on to see how they are used to construct various linear combinations.